So not only are derivatives defined as limits, but we can also define continuity as a limit. Now, up to this point, before you knew about limits, you're always told continuity meant that you could just draw the graph without any breaks or jumps. That's kind of a geometric intuition of what a limit should be. But we can also give this very precise definition for what it means for a function to be continuous, first at a point and then on some interval or in some range. So if the limit as x tends to c of f of x actually equals the value of f of c, in other words, if as the inputs get close to c, the function gets close to its value at c, then we say the function is continuous. Now, in order for that to work out, there are really three things that have to happen. First, f of c has to be defined. So if f isn't defined at c, there's no hope of it being continuous. Also, the limit as x tends to c of f of x has to be defined, and we've seen that the limit doesn't always exist for certain functions. So for example, if there was a break or a jump or some other weird things, so the limit has to be defined, and they have to agree, right? They have to be equal. They have to agree that what you get close to, as the input gets close to c, what comes out of the function actually gets close to what comes out of the function at c. So those two must agree. Now, that's what it means to be continuous just at this single point c. So at a point c, if we just want to talk about a function being continuous, then we say that it means it's continuous at every point. Or we could talk about being specifically continuous on a particular interval, if it's continuous at every point in the interval. Now, there's a little bit of an allowance for the endpoints. Let me explain. If we look at the graph of this function is obviously continuous at every point between a and b, because if you pick any value, let's say c right here, as the if you plug in c, out comes this value, whatever it is, f of c, and you can see that as the inputs, let's say you have some input x, the closer that input gets, right, as the inputs get close to c, the outputs get closer and closer to f of c. So it's continuous at every point in here. The one place where the limits might not exist would be at the endpoints, right? Obviously, the limit as x tends to a from below of f of x doesn't exist because f of x isn't even defined over there. So, but when we're talking about being, I really misspelled that. So the limit as x tends to a of f of x doesn't exist. When we're talking about the endpoints of an interval, we make a little bit of allowance. As long as if you're at the left endpoint and the limit as you come down to a from the left exists, then we'll go ahead. That's the little allowance that we make for endpoints of intervals. Same thing here. Since b is the right-hand endpoint, as you come up to the right-hand endpoint, the limit does exist. And so we'll say, well, that doesn't really make it discontinuous. But if there was a point in here where the function wasn't defined, so that there was a little hole in the graph, then of course the limit wouldn't exist, right? Because the function wouldn't even be defined, then of course it wouldn't be continuous, because even though the limit, let me give this point a name, maybe e, even though the limit as x tends to e of f of x exists, f of e does not. And remember, the limit had to exist, the function had to be defined to the point, and the two had to agree, and so we stop there. You could even have a function that had like a jump. I could give the function some other value at e, then f of e would exist, but the limit and the value don't agree, and so this function's not continuous. Of course, if we had a jump in our function, then the limit wouldn't exist, and so we wouldn't be continuous, because the limit has to exist, the function has to be defined at the point, and the two have to agree for it to be continuous. But as it was drawn, before I put that little hole in there, as it was drawn, f is continuous. This will be my little abbreviation for continuous, to say continuous, slur it a little bit. F is continuous on the whole interval from a to b. We could contrast that with this function. This function is continuous everywhere. If I give this function the name f again, this function is continuous on the open interval. It's continuous at every point between a and b, but it's not continuous on the closed interval, because it's not continuous at a or b. So the reason that it's not continuous at a or b is because the function is not even defined at a. You try to plug in a and there's a hole, you shoot through, you never cut across, so you never get an output on this function. So okay, so we kind of understand continuity here. Now there's a relationship between continuity and differentiability, and this is how it works. Remember, for a function to be differentiable, this limit has to exist. But this limit, if it's going to have any hope of existing, it needs to turn out to be 0 over 0. It needs to be indeterminate so that hopefully it would simplify and we could find some kind of limit. If f of x doesn't get closer and closer to f of c as x gets close to c, then there's no hope of this limit being some finite number. So the point is that if the derivative exists, then it's just going to have to be that the function is continuous, because in order for this limit to exist, definitely f of x has to be getting closer and closer to f of c. If not, then we would have like some non-zero value divided by a value that's getting smaller and smaller. It's going to blow up on us in some way. So definitely for the derivative to exist, the function has to be continuous. But it doesn't go the other way. A function can be continuous and not have a derivative. So just because a function is continuous doesn't mean that it's differentiable. So it's important to keep those in mind. Let me show you some examples. Well, first, this function is definitely continuous, right? But it's not differentiable here. So here's an example of a continuous function. It's not differentiable. Here's another example of a continuous function, right? You can draw it with no breaks or jumps, definitely continuous, and yet it's not differentiable because of this cusp, right? It's not differentiable at this point. So just because it's continuous, even though it's continuous at 1 even, right? As the inputs get close to 1, the outputs get close to -1, so which is f of -1. So it's definitely continuous, but it doesn't have a derivative there. So just because it's continuous doesn't mean it's differentiable. Although if it had been differentiable, we would know automatically it was continuous. This one is continuous but not differentiable because it has a vertical tangent right there.